In huge news for astronomy fans, James Webb may have made an intriguing breakthrough in the field of space exploration. The Supreme Observatory has just made a groundbreaking discovery light years outside our solar system, when capturing city lights 7 trillion miles away from Earth. This remarkable finding then sparked curiosity about the possibility of extraterrestrial life. But after all, has James Webb really found life beyond Earth? Join us as we dig deep into Webb's stunning discovery that could blow your mind. In January 1992, 2 radio astronomers announced a discovery that would change our view of the universe forever. Alexander Wolszczan had been scanning the skies to study a type of spinning star known as a pulsar, but something was blocking his view. Curiosity piqued, Wolszczan eventually discovered the root of the interference: 2 planets in orbit around the star. Fellow radio astronomer Dale Frail verified the data, and the pair made their incredible announcement to the world. They had discovered the first ever known extrasolar planets, or exoplanets. The existence of exoplanets, planets orbiting stars other than our Sun, had long been theorized, but now there was definitive proof. For the first time, humanity could be sure that the solar system in which it lived was not alone. There were planetary systems out there in the cosmos. Since this discovery, there has been a concerted effort by astronomers to find even more of these exoplanets. At last, through a combination of strong instruments like NASA's Kepler Space Telescope, we've surpassed 5,000 known exoplanets. As is often the case, these discoveries have been tremendous and have answered some of our deepest questions about the cosmos. Nevertheless, even deeper ones now remain. That's why now, a new generation of exoplanet hunting missions is conducting for follow-up investigations to build on Kepler's progress and make discoveries that could change what we know about how planets form and how life might arise elsewhere in the universe. Perhaps most exciting is the James Webb Space Telescope. James Webb is seen by many as the successor to the Hubble Space Telescope, albeit 100 times as powerful, and rather than orbiting Earth, will instead orbit the Sun at a distance of 1.5 million kilometers from our planet. This helps it avoid heat from the Sun, Earth, and the Moon, and remain cool, around -225 degrees C. Why? Because warm objects emit infrared light, and infrared is the primary method of Webb to observe the universe. One of its goals will be to observe young planets forming around young stars. Stellar formation begins when clouds of gas and dust in space begin to clump mass together, growing so big that they eventually collapse under their own gravity. What remains is a young protostar surrounded by a spinning disk of dust. Out of this dust may form a system of planets orbiting the central star, just like our own solar system. In optical light, these still-forming planets are obscured by the dust, but infrared can peer through it to get an unprecedented look at planetary formation in action. As Dr. Jane Rigby, one of the mission's project scientists, said, "We build space telescopes because they can take sharper pictures, due to the fact that Earth's atmosphere is not in the way distorting what we're trying to see. If we want to study most colors of infrared light, then we need to go into space because that light cannot shine through our atmosphere." What's really exciting is Webb's ability to split starlight, a technique known as spectroscopy. By splitting the starlight that has passed through the atmosphere of an exoplanet, scientists can analyze the chemical signatures hidden within and learn much about the properties of that exoplanet, whether it has a lot of water vapor in it or other chemicals that might reveal something about the processes occurring on its surface. In the word of Rigby, this is our first chance to understand in detail the atmospheres of exoplanets, and there's a lot of interest in studying rocky planets like our own. And just as expected, more than 2 years after operation, astronomers are using the telescope to look for life on thousands of newly discovered planets. There is a distant world where quartz crystals float above a searing, hot, puffy atmosphere. Vaporized sand grains, not water droplets, form the clouds that fill the sky on WASP 107b, a planet 1,300 light-years from Earth. Then there is GJ 1214, the sauna planet. With a mass 8 times that of Earth, it orbits its parent star at a distance that is 1/70th of the gap between Earth and the Sun, and seems to be coated in a thick, dense atmosphere containing vast amounts of steam. Or there are the giant, Jupiter-sized planets of the Orion Nebula, which have been discovered free-floating in space, rogue worlds that appear to be unconnected to any parent star, to the bafflement of astronomers. These strange, remote planets could not be more diverse or dramatically different from each other, although they do share one common feature. Their wonders are now being revealed by the James Webb Space Telescope. Of course, those discoveries are just the tip of the celestial iceberg. Crucially, several hundred are relatively close to Earth, and these are now ripe for study with the James Webb. One of them is Proxima Centauri, the closest star to our Sun. We've carefully observed it for both radial velocity and transiting imperfections, looking for any sign of a planet around it. Proxima Centauri is a tiny, low-mass red dwarf star, emitting just 0.17% the radiation of the Sun. There are many ways that the star is different from ours, being smaller, cooler, flaring far more often, and the fact that it will live not for billions of years, like our Sun, but for trillions. Proxima Centauri is also part of a trinary system, where the two main components, Alpha Centauri A and B, are roughly Sun-sized and orbit one another relatively close by, but Proxima Centauri is much lower in mass, cooler, and more distant. When we observe Proxima Centauri, we don't see any evidence for a transiting world, and any planets that are there are far too dim to be seen with direct imaging and our current technology. But we do see the signatures from radial velocity of a single, massive world that orbits it. From the observations we've made, we can determine the following properties of this planet, now known as Proxima b. It has an orbital period of 11.2 days. The amount of starlight it receives from Proxima Centauri, 65% of what we get here, should give it Earth-like temperatures if it has an Earth-like atmosphere. It has a minimum mass that's 130% the mass of Earth, just a little more massive than our planet. There may be other planets present as well, either lower in mass and/or with much longer orbital periods, which our observations are not yet sensitive to. But this one, at least, is real. But what is it like? Is it Earth-like? There are many ways we know that it must differ from our planet Earth, including it must be tidally locked to its star, where the same face always faces the star and the same face always faces away. It will have 3 climate zones, an ultra-hot one where it's always sunny, an ultra-cold one where it's always night, and an on-the-border one where it's always sunset-sunrise, and the solar flares coming from the star will potentially be a danger for stripping the atmosphere away. We can, of course, concoct scenarios where the planet hangs onto or replenishes its atmosphere and has conditions conducive to life. But this is nothing more than wishful thinking. In reality, we do not even know whether this planet is Earth-like or Neptune-like. The typical border between an Earth-like world, where you have a rocky surface with a thin atmosphere, and a Neptune-like world, where you have a large gas envelope surrounding your world, is about 2 Earth masses. Proxima b has a minimum mass of about 1.3 Earths, but that's if the alignment is perfectly edge-on. Since there's no transit, we know the alignment cannot be exactly perfect, but how imperfect is it? That's gloriously unknown. If the alignment is inclined at more than about 25 degrees from our line of sight, it's likely to be a gaseous world, not a rocky, Earth-like one. But at this point, without further information, we cannot know. If we were going to be as accurate as possible, we would state that there is a planet with an orbital period of 11.2 days orbiting the closest star to us, Proxima Centauri. It receives 65% of the solar energy that Earth receives and has a minimum mass of 130% the mass of Earth. That's it. That's all we know for certain. If we wanted to speculate, we could discuss all the reasons Proxima b is likely to be inhospitable to life. What challenges this planet faces if it wants to achieve habitability, and what we'd have to measure to know for sure. But the truth is that we don't know any more than this. Until James Webb has better, more comprehensive data on this world, all we know is its period, the energy it receives, and its minimum mass. The age of exoplanet astronomy is upon us, but it's still in its infancy in many ways. Wonder about the possibilities and feel free to speculate as to what might be out there, but never conflate your hopes with what's actually likely. The only way to know for sure is to build the right instruments and observatories and take the critical data. The only way to know what's out there for certain is to find out for ourselves. And as told, Proxima b is not the only exoplanet that caught James Webb's eyes. In a previous finding, the observatory centered on a world known as K2-18b, a planet orbiting a faint red star some 120 light-years from Earth. Data from Hubble and James Webb show a giant planet, roughly 8 times the size of Earth, but one that seems to have an atmosphere rich in hydrogen and a surface covered in deep oceans. More intriguing, data published last year claimed the Webb telescope had found evidence of dimethyl sulfide in K2-18b's atmosphere. On Earth, this chemical is a certain sign of life, and so, to find it floating through the air of a distant planet is interesting, to say the least. Add that to earlier speculation that K2-18b is a Hyson world, a hypothetical type of planet that could be habitable, and you have all the ingredients for a groundbreaking claim of alien life. Still, caution is to be advised. No Hysian world has ever been definitively found, and some argue that they do not really exist at all. Even if they do, it is not certain K2-18b is one. And the signature of dimethyl sulfide was weak, so weak, in fact, that it might not be there at all. 3 questions, then, surround this world. Is it really a Hysian world? Is dimethyl sulfide really present in its atmosphere? And if it is, does that definitely imply the presence of life? Those are hard questions to answer, and what answers exist is often controversial. Thus, to solve the riddles, we need more data. That could come from the James Webb, which might be capable of better resolving the signal with more time. But it may need to wait for the next generation of telescopes, some of which will be designed to sniff out such chemicals with much greater precision. Either way, it is still too early to settle the question of dimethyl sulfide. Regardless, one thing can't be denied. The Webb Space Telescope now is the largest, most powerful, and most complex telescope ever launched into space, and its results have surpassed all our expectations. In a recent observation, the Webb telescope has performed a weather report for a distant planet. The powerful space telescope forecasts extreme wind speeds, blisteringly hot temperatures, and blankets of rock clouds for the world, named WASP-43b. As such, the extrasolar planet, or exoplanet, demonstrates just how strange alien planets outside the solar system can be. WASP-43b orbits a star located around 283 light-years from Earth. It sits so close to its star, in fact, that it completes an orbit in just around 19 Earth hours. This proximity, equal to around just 1.3 million miles, 2.1 million kilometers, means the planet, with a mass around 1.8 times that of Jupiter and a width 0.9 times that of the gas giant, is tidally locked to its star, WASP-43. Thus, one side of WASP-43b, its day side, permanently faces the star and is constantly bombarded by radiation, sending planetary temperatures soaring to around 1250 degrees Celsius. That's hot enough to melt lead. The other side of the planet, its night side, faces permanently out into space, resulting in temperatures falling to a relatively chilly 600 degrees Celsius. These qualities mean WASP-43b is classified as a hot Jupiter planet. The James Webb Space Telescope, transiting exoplanet early release science team, was able to use the telescope's MIRI to classify the climate of WASP-43b and the type of weather it experiences on its day and night sides. As team member Laura Kreidberg, director at the Max Planck Institute for Astronomy, said in a statement, "With the new observing power of JWST, WASP-43b has been unveiled in unprecedented detail. We see a complex, inhospitable world with furious winds, massive temperature changes, and patchy clouds likely made of rock droplets. WASP-43b is a reminder of the vast range of climates that are possible on exoplanets and the many ways in which Earth is special." WASP-43b was discovered in 2011 because of a dip in the light scientists saw exhibited by WASP-43. This dip occurred as the planet crossed between the face of its star and Earth from our perspective. During the transit, scientists also saw that infrared light the planet emits in response to starlight varied. The main result of Webb's investigation of WASP-43b was thanks to this infrared light variation observed between the day side and the night side of the exoplanet as it orbited its star. The variations, more particularly, helped scientists build a map that shows how temperatures are distributed across the entire hot Jupiter. Ultimately, the team found the variation in temperature between day and night sides of WASP-43b is too great to be seen in an atmosphere bereft of cloud cover. However, any possible clouds above WASP-43b's surface are not likely to be water-based, like those enshrouding Earth. They wouldn't even be ammonia clouds like those we see around Jupiter. WASP-43b is just too hot for either. Rather, this world's clouds might be made of rock. Vaporized material, such as rock, is carried from the day side to the night side of WASP-43b by powerful winds reaching speeds of 5,600 miles per hour, 9,000 kilometers per hour. That's 3.5 times as fast as the top speed of a jet fighter here on Earth. Then, once on the night side of the planet, scientists believe this material cools and condenses. This means the thick cloud cover on the night side of WASP-43b is likely composed of droplets of liquid rock that had vaporized on the planet's day side. To that end, the researchers found that the day side of WASP-43b appears to be cloudless. To determine the composition of WASP-43b's atmosphere, the team split the observed infrared light into separate wavelengths, thus creating what's known as a spectra. Because chemicals and elements absorb and emit light at characteristic wavelengths, they leave behind fingerprints in such spectra. As Taylor Bell, team leader and a scientist with NASA's Ames Research Center, said in the statement, "With Hubble, we could clearly see that there is water vapor on the day side. Both Hubble and Spitzer suggested there might be clouds on the night side, but we needed more precise measurements from James Webb to really begin mapping the temperature, cloud cover, winds, and more detailed atmospheric composition all the way around the planet." Not only did James Webb's investigation determine that water vapor is found all over WASP-43b on both its hot and cooler sides, but it allowed the scientists to see a lack of methane in the planet's atmosphere. Hot Jupiters are normally expected to produce water and methane on their night sides via reactions between hydrogen and carbon monoxide. The team thinks WASP-43b lacks methane because its raging winds pass these reacting molecules through the night side of the planet too fast for the molecules to react with anything and create methane in detectable amounts. Any small amount of methane that is created would probably mix with other gases and quickly get carried to the planet's day side, where intense heat destroys it. James Webb isn't done with WASP-43b just yet. A separate team is currently using the $10 billion telescope's NIR SPEC instrument to perform a follow-up study of the planet. Not only should this improve the MIRI temperature map, but these observations should also lead to measurements of gaseous carbon monoxide in the atmosphere of WASP-43b, providing a better overall picture of this extreme world's chemical composition. In a recent eye-catching observation, the James Webb Space Telescope has captured incredibly sharp images of the Horsehead Nebula, one of the most iconic celestial bodies in the sky over Earth. The Horsehead Nebula, also known as Barnard 33, is a collapsing cloud of dense, cool gas that is illuminated by a hot young star embedded in its top left edge. The horse-like structure that makes this nebula so distinctive has been created because lighter gas has been eroded. This has left a thick pillar of dense gas and dust that is harder to erode. This won't last forever, though. Scientists estimate that in around 5 million years, even this pillar of denser matter will be gone. And as the most powerful telescope ever placed into orbit around our planet, the Webb telescope was able to see details of the Horsehead Nebula that had never before been revealed, showing some regions in a completely new light. The new images show the Horsehead Nebula as turbulent waves of gas rising from the western side of Orion B, a star-forming molecular cloud located 1,300 light-years from Earth in the constellation of Orion. And as a worth note, the Space Telescope Science Institute has announced which astronomy proposals have been selected to be given time with the James Webb Space Telescope over the next 2 years. One of the teams lucky enough to get time with James Webb during Cycle 3 will be searching for moons outside the solar system. These are known as extrasolar moons, or simply exomoons. Thus far, exomoons have proved an elusive subject for astronomers because they are hunted using the same light-blocking technique employed to spot exoplanets around stars. However, this technique is difficult enough when looking for large worlds beyond Earth. Searching for little exomoons with it is immensely challenging. Not only would exomoons block far less light than the exoplanets they orbit would, but they'd also need to be in the right position at the right time. An exomoon that's detectable would have to be orbiting its planet precisely as that planet's crosses, or transits, the face of its parent star, to obscure some light when viewed from our vantage point in the cosmos. That obstruction would be detected by scientists' equipment, which would allow them to reverse calculate that an exoplanet, or potentially exomoon, gave rise to it. David Kipping, an assistant professor of astronomy at Columbia University, is part of the team that hopes to find moons around the exoplanet Kepler 167e in particular. This gas giant is around the size and mass of Jupiter and is located 1,115 light-years from Earth. In the words of Kipping, Kepler 167e is the best target we've ever had for moon hunting. So, he is hoping that, by focusing on Kepler 167e with Webb's near-infrared imager and slitless spectrograph, he and his team can make the first undisputed detection of an exomoon. This is hopefully just the beginning of the exomoon revolution, new worlds that will surely hold some remarkable secrets, Kipping said. Of course, Webb's Cycle 3 GO projects also include a wealth of investigations focusing on exoplanets themselves and not just their potential moons. This includes a few that wish to determine whether some exoplanets have the conditions needed to support life as we know it. Among those exoplanet habitability projects is one called Constraining the Atmosphere of the Terrestrial Exoplanet TOI 4481b. This will use Webb's MIRI for 16 hours to determine if a roughly Jupiter-mass exoplanet, which orbits a star around half as massive as the Sun that sits some 39 light-years away, has been able to hang on to its atmosphere. The result could serve as a first step in understanding the habitability of rocky planets and establishing whether M-type stars, also known as red dwarfs, have terrestrial planets with significant atmospheres. This is important in the search for life beyond Earth, because red dwarfs are the most common stars in the Milky Way. In addition, astronomers widely believe the majority of our universe's large galaxies have supermassive black holes in their hearts with masses as great as millions or even billions of suns. Some of these supermassive black holes are actively swallowing gas and dust that surrounds them in disks of matter, called accretion disks. These monster black holes' gravitational influences are thought to heat the material in those accretion disks, causing them to emit bright radiation across the electromagnetic spectrum and create regions called active galactic nuclei, AGN. Additionally, Any matter that isn't swallowed by the black hole can be channeled to its poles, where it is blasted out as jets of particles traveling at speeds approaching light. When that happens, the phenomenon is called a quasar. The violent conditions of these events make AGNs and quasars the brightest objects in the universe, often luminous enough to outshine the combined light of every star in the galaxies around them. Our theoretical understanding of supermassive black holes has burgeoned since the Event Horizon Telescope, EHT, revealed the first image of a black hole, the supermassive black hole at the heart of the galaxy Messier 87, M87, in 2019. And James Webb's Cycle 3 missions will further contribute to this knowledge. The Cycle 3 supermassive black hole observation programs include the investigation of quasars in the early universe and the nature of the first black holes. Scientists hope to understand how those black holes may have influenced the growth of galaxies over billions of years. Webb's observations of supermassive black holes in the early universe could also reveal how these cosmic titans grew to the tremendous masses scientists observe before the universe was even 1 billion years old. Such a question can be answered by using MIRI to investigate if a giant molecular cloud that existed around 13.2 billion years ago could have directly collapsed, birthing a heavy black hole seed that would account for a rapid growth mechanism. On the other hand, one of the primary roles of the James Webb Telescope is investigating objects in the early universe. The powerful space telescope has this capacity because the expansion of the universe stretches wavelengths of light from distant objects as this light travels toward us, moving the wavelengths toward the red end of the electromagnetic spectrum. The longer that light has traveled to reach us, the more red-shifted the light has become. This means light that has been traveling for around 12 billion years is extremely red-shifted, all the way into the infrared region of the electromagnetic spectrum and outside the visible range we can see with the unaided eye. Effectively, infrared light is invisible to us. However, the observatory is capable of observing this infrared light and thus helps to investigate the first stars and earliest galaxies, something it will continue to do in 2025 with several Cycle 3 GEO projects. That's why cosmologists are particularly enthusiastic about GO projects that will look at an era of cosmic evolution called the Epoch of Rionization, which occurred around 500 million years after the Big Bang. During this period, neutral atoms of hydrogen populating the cosmos were ionized by radiation that stripped away their electrons and left them as ionized hydrogen, or hydrogen ions. Studying high redshift galaxies can reveal more about this crucial stage in cosmic evolution, including how the first galaxies acted as the source of this ionizing radiation. Some of the proposals that catch their interest are understanding galaxy formation at cosmic dawn, galactic winds in the early universe, and dead or alive, unveiling the nature of massive galaxies in the early universe. All of these accepted projects seek to identify and characterize galaxies that are the drivers of the epoch of Rionization. Of course, this is just the tip of the celestial iceberg when it comes to the range of topics Cycle 3 GO projects will cover. Between 2024 and 2025, astronomers will also train telescopes on distant stars to better understand stellar physics and populations, as well as examine the gas that exists between stars that can become the building blocks of the next generation of stars and planets. And though the Webb telescope was designed with the study of distant objects in mind, Cycle 3 will also see the observatory used to study bodies within our own solar system. These will include hunting for the source of gas plumes coming from Saturn's moon Enceladus, investigating the dynamics of the Uranus's rings, and characterizing icy objects that exist in the Kuiper Belt at the very edge of the solar system. Looking beyond James Webb Cycle 3, the call for Cycle 4 GO proposals will go out on August 1, 2024, with a deadline set for October 16 this year. The Cycle 4 Telescope Allocation Committee review will run between February 3 and February 12, 2025, with selections revealed around March 5 next year. Webb's Cycle 4. Go programs will then begin making observations of the cosmos on July 1st, 2025. That's all the information that we have for you today. Don't forget to give us a thumbs up if you enjoyed today's episode, subscribe if you haven't already, and hit the bell so you never miss out on future episodes. And be sure to also tell us what you think about today's content. Everyone's support motivates us to continue delivering quality content and to always improve. As always, thanks for watching, and we will see you next time.